building, and we have a blast and impact facility, what we call the Extreme Event Simulator facility on the right. These additional facilities are not a part of the NHERI program. NHERI is short for Natural Hazards Engineering Research Infrastructure. It's a program run by NSF. They fund the operations at our facility. So the Soil Structure Interaction Facility and the Blast or Impact Facility are not part of the NHERI program, but they are available to users on a recharge basis. So if there's a research group that would like to use them, they can. We are IAS accredited, so all the data that's produced from experiments at our facility is accepted in over 80 countries around the world with no questions asked, and that's something we take pride in as well. So talking about the shake table itself. So in the past, we called it, for the past 20 years, we called it the LH Post, the Large High Performance Outdoor Shake Table. It was designed back in 2001 to 2003, built and commissioned in 2004. From 2004 until 2014, it was funded by the NEES program over at NSF, so we called it the NEES at UC San Diego. 2016, the NEES program, 2015, the NEES program ended, and on 2016 through 22, we became part of what is now known as the NHERI program, also funded by NSF. Somewhere in the middle there, back in 2018, we were awarded a large grant from NSF and additional funds from UC San Diego to perform this upgrade, to take the shake table to the 6th degree of freedom. So we had the upgrade project ongoing during COVID, which was a big challenge, but we finished it and commissioned the shake table last year in 2022 as a 6th degree of freedom. And we were awarded a renewal for our NHERI program from 2022 through 2025. So we are fully supported by the National Science Foundation. The original shake table, the original LH Post, was designed back in 2001 to 2003-ish. It was designed with 6 degrees of freedom in mind. Originally, we wanted it to be a 6 degree of freedom shake table, but the funds were limited at the time, so we couldn't build it as a 6 degree of freedom. So it was built as a single degree of freedom, only in the longitudinal axis. There's some specs here on the screen, but we're just going to gloss over them because these are old now. Just important to note that it was always intended to be a 6 degree of freedom shake table. For the past 15 years running the table in the 6 degree of freedom configuration, we were very proud of the tracking ability and the reproduction ability, the quality of how we would reproduce earthquakes. You can see here we're looking at the acceleration on the top, where it's zoomed into it a little bit. The target and the achieved are pretty near identical, and we were very proud of that performance. So we had to keep that in mind when we wanted to upgrade to 6 degrees of freedom, because we still wanted to maintain that level of quality and that accuracy. In addition to just the shake table where you can build your specimen on a building or some sort of infrastructure on, we also have 2 large soil boxes that are available to users. Now there's 2 different ones here. There's the brownish colored one. That's a laminar soil box where it can allow shear deformations in the soil. You can use bladders and saturate the soil for some liquefaction tests. You can put it at an incline on the shake table. Many different use cases there. And then on the right, we have that stiff soil box where you can do many different types of testing. You can put columns inside that box and retaining walls and things of that nature as well. And these have been really popular at our facility for the past 15 years. And it's important to note that they're still available to the users. So over the past 15 years in the single degree of freedom configuration, we successfully completed 34 large landmark projects, both commercial and research. This is just a small set of those projects that you can see here. It ranges from tall buildings that are reinforced concrete or timber. We got those soil boxes there. There's a wind turbine that has been tested, unreinforced and reinforced masonry buildings, steel buildings. All sorts of different types of experiments have been conducted using our shake table. 34 in the single degree of freedom, and since last year, if you were to include this most recent project in the 6 degree of freedom, it's 35 landmark projects. So we keep talking about this upgrade. What have we done? So I don't have any photos, because it's really difficult to capture photos down there that can really show the picture. So I have this little rendering here to show the hydraulic power system of the LH Post 6, as we're calling it now, for 6th degree of freedom. Everything had to be torn out and replaced, aside from the shake table platen itself, which we can still use. It's 40 feet by 25 feet. We also were able to keep the surge tank. You can see, I don't know how to get this on, sorry. You can see it at the top of the screen over there. We kept the surge tank. We were able to keep 2 of our hydraulic power units, those large pumps that would pressurize the accumulation system. But everything else had to be torn out. We had to quadruple the size of our accumulator bank because of the amount of oil we needed at high pressure to be able to reproduce these near field ground motions. All the piping had to be torn out and replaced with larger diameter piping, and actually increased substantially because now we have 6 vertical actuators and 4 horizontal actuators that all need to be powered by high pressure oil. So we had to form an entire ring around the shake table platen to be able to bring that high pressure oil to each one of those actuators. So you can see the red and the blue ring that goes around all the little equipment there. It's kind of small. I don't expect anyone to be able to see what those are, but it shows the 6 vertical actuators. You can't see the 4 horizontals in this photo, so I'll show another photo later. But those large, darker rectangular stacks in the upper right corner are the accumulator banks. So the accumulator banks consist of 75 bottles, each 130-gallon capacity. They're pre-filled with high-pressure nitrogen at 3,000 psi. And the way the system works is those hydraulic power units, those pumps, pressurize these accumulator bottles to 5,000 psi. And we have 6 large blowdown manifolds that can release that high-pressure oil at a regulated 3,000 psi to the actuators and perform the motion. Now, this is very critical. This accumulator system is critical, and we need to monitor it to make sure that there's no leaks and it's performing the way we want it to perform, especially since we're dealing with high pressures. So we have wireless sensors installed on every single bottle that gather pressure, temperature, and other data metrics, and we keep it in our server, and we track it over time. We do trending, and we also look at it in real time. Some of the observations that we've made over the years has been that temperature fluctuations during the day actually affect the pressure inside these accumulator bottles quite a bit. So that's very important for us to know. If you were to take a snapshot in time, if you just go look at the pressure and you see that it's low, you might overcharge the system and cause problems. So you need to be cautious, and having this tracking and databasing ability is very important. One last rendering here just to show you what it would look like if you were there. Hopefully you will be able to come join us there one day and we'll give you a tour. This is a little SolidWorks model, and it's just a longitudinal cut. So you can see the 4 horizontal actuators. There's 2 on each side in a V shape, and there's 6 vertical actuators that you kind of can't really see in this photo underneath the shake table. 3 on the north and 3 on the south. So the performance characteristics, again, I have this table. Don't expect anyone to read it, but the important things I try to highlight in yellow. The large block with the data inside, it's actually split into 2 columns, 2 main columns. The 3 columns on the left are with bare table, and the 3 columns on the right are assuming you have a rigid payload of 1,100 kips on the shake table. Just to see the performance of the system when it's loaded versus unloaded. The things I'd like to highlight here, again, this is probably very small. The displacement limits doesn't change with loaded or unloaded. We have plus or minus 35 inches in the X or longitudinal direction. We have plus or minus 15 inches of travel in the lateral or Y direction, and plus or minus 5 inches in the up and down. And for the velocities, we are very proud that we can achieve 118 inches per second in the longitudinal, 90 inches per second in the lateral, and 17 inches per second in the up and down. Now, the only thing that really changes between the loaded and the unloaded table is the velocities that we can achieve on the loaded table actually increase because of the nature of the way our vertical actuators are designed. They're single acting, so they can only push up and rely on gravity and external forces to bring the system down. So if you're loaded on the table, if you have a load on the table, that actually helps the performance of our system. So really quickly, just to show the same or similar plot that I showed earlier with a single degree of freedom, here we have three plots on the top are X, Y, and Z acceleration. The lower ones are X, Y, and Z velocity, and then to the right you have X, Y, and Z in displacement, and you can see that our accuracy is still very, very good, and we are able to accomplish quite great results from the shake table. I do have to say that this was, this data is from our acceptance testing when we were doing the acceptance testing, and it was bare table. Once we load the table, things get a little more complicated, and we'll see the performance of those. But this is still fantastic. Now I'll just show you a few brief videos. I see I'm running out of time. They're only like 20 seconds each. This is an AC 156 compatible earthquake, triaxial, and we can use this motion for a lot of qualification testing. Why is this not playing? All right, well. Yeah, I guess we can't show you the videos. So I had another video here for Tabasa earthquake. It's also another triaxial, and one synthetic 6 degree of freedom motion that I really wanted to show, but I don't know, for some reason it's not working. I don't know if you want to help me out here, if you don't mind. I can't even see my mouse cursor. So. Oh, there we are. How'd you do that?
So what's there?
Ah, gotcha. Thank you. So you can see this one is the 6 degree of freedom. It's a synthetic motion, but it's a good demonstration just to show the capability of this system. The rotational degrees of freedom, even though we can move, let's say, 1 or 2 degrees, they seem very small, but when you look at it, it looks pretty impressive. And while we're here, now that I can play it, I'll play this one, the Tabas earthquake. It's a triaxial motion, pretty good earthquake. It's a magnitude 7.4. And this is replayed in 3D. All right, my time is almost up, so just one more short video and I will wrap this up. This is the recent 10-story building testing that we completed, Loma Prieta earthquake, MCE level. It was done in May 17th. It looked really cool. All right, I'm just going to skip over the remainder of the slides. I would like to just put a little plug. If you have any questions or want to gather more information, come join us. We have a workshop in December. It's December 14, 15. It's in San Diego. We can't go wrong with San Diego in December. Please join us. Registration is going to open up pretty soon. You can check us out on the website or email me or any one of the PI or co-PIs at our facility. We're more than happy to answer any of your questions. Thank you.